we dive deeper into the world of trigonometry, we find that there are real-world problems that include trigonometric terms. That means you can express an equation or you can model a situation using trigonometry. Some relations among trigonometric ratios are always true. So we're going to write down a couple of these trigonometric relationships that are always true, and they're called trig identities. They're things that we can use and switch out and consider as equal in any trigonometric problem that we're working in. They're called trig identities, an equation that is always true regardless of the value of the variable. So, an identity. This is an equation that is always true regardless of the value of the variable. So when we're using trig identities, it means we can trust that they're going to be true, that that we are able to swap out the left side for the right side of the equation anytime in any problem. Okay? Some of the basic ones that we're going to be working with that we already know, one of them is reciprocal identities. Okay? The reciprocal identities, well, that's just the reciprocal trigonometric ratios. We know that the cosecant of theta is equal to 1 over the sine of theta. And that's true no matter what angle you're talking about. The other two are the secant of theta, which is the reciprocal of cosine. Again, this is a trigonometric identity. This is going to be true no matter what the angle measurement is. And cotangent of theta is equal to 1 over the tangent of theta. Then we have the quotient identity. And we've never used this name for it, but it's also very straightforward. You already know it. It is sine of theta over cosine of theta is equal to the tangent ratio of theta. This will always be true no matter what the angle is. We're familiar with using that one already when we're gathering our exact values in the unit circle. The last one we have not used yet, but comes very handy, Pythagorean identity. The Pythagorean identity says that the square of the sine of theta plus the square of the cosine of theta is equal to 1. That one I'm going to just very briefly explain for a second. It's not difficult, but I just want to draw a little picture to help us get the understanding of it. Basically, when we took any point on our unit circle, 1, 1, negative 1, negative 1, we found out that the coordinates were cos theta, sine theta. Okay, that's familiar. That means that the distance that you traveled along the x-axis was equal to cos theta, and the distance traveled along the y-axis was equal to the sine of theta. Now I'm drawing my triangle a little bit backwards here, but what you can see, if I finish off, the hypotenuse here in the unit circle is always 1. So right here you have it, x squared plus y squared equals 1 squared. That's the Pythagorean theorem in a right angle triangle. Well, here x is cos of theta and y is sine of theta. So if I take the square of that, and added to the square of that, I get the square of that. Well, it's the square of 1 is 1 times 1 is 1. So the Pythagorean identity is really just the Pythagorean theorem pulled right out of that unit circle. The square of sine of theta plus the square of cosine theta is equal to 1. Just one more note if you're not really sure why it's written like this. What this really means is taking the sine of theta and squaring it. But because in longer or more difficult problems, or when we're working through these proofs, which we're going to be doing, this becomes a bit tedious and a bit messy, and there's no other meaning for this, I guess, sign or symbol or whatever it is, this way of writing something. They said, okay, well, instead of writing it like this, that would be just fine, but let's write it like this. It's just easier. This is the square of the sine of theta, okay, which makes this the square of the cosine of theta, okay? Keep that in mind as we work through. Now we're going to be doing a few proofs today as examples, and you have loads of trigonometric proofs to do applying these identities over the next couple of days, and it really is a problem-solving activity. It's figuring out, like a puzzle, a way to do and undo and manipulate in order to prove a given trig statement, okay? So we're going to be working in proper format, left side, right side, which we'll explain in a moment as we're going through our examples. And really it's just going back to these three tools and saying, okay, algebraically, what now can I do to left side and right side to see if they are indeed equivalent. In order to prove trig identities, we're going to be following four main steps that are there, okay? First of all, we're going to be using proper right side, left side, maybe we would do it like that, right side, left side form, okay? Then we're going to look at our strategies for actually proving things. The first thing that we're going to look for is reciprocal ratios, and we're going to replace them with primary trig ratios. So replace reciprocal ratios with primary trig ratios. That would be applying that reciprocal identity. The third thing we're going to look for is any tangent ratios, and we're going to replace tangent ratios with sine over cosine. That's your quotient identity. And then we are just going to use basic algebra techniques okay, that's addition, subtraction, multiplication, division, squaring, square rooting, factoring maybe, working with fractions maybe, distributive property maybe. Okay, so all those tools that you already have in your toolbox that you've applied to integers, to just regular numbers, and also algebra variables, we're going to apply those to our trig identities. So I'm going to leave those up there, and it would be a good idea to kind of always have those steps in mind. So number one, once you get used to having left side, right side format, then what you're saying is, okay, are there any reciprocal ratios? How do I get rid of them? Are there any tangent ratios? How do I get rid of them? Okay, work from here using basic algebra. In example 1, we're asked to prove that the square of the tangent of theta plus 1 is equal to the secant of theta squared, okay? So we're already told that this is true, but we're going to prove that it's true. We're going to make sure. In order to do that, we're going to use our formatting, left side, right side. Should be somewhat familiar with this, but on the left side, I can see I have the tangent of theta squared plus 1. On the right side, I have the secant of theta squared. Now, if I can work down one of these sides or both of these sides, and at the end I end up with the same statement, then I can say left side equals right side and check mark, I've proved it. Okay, I'm going to start this time just working down the left, and we're going to follow those rules that we have. I don't have any reciprocal trigonometric ratios on the left, but I do have the tangent ratio. So I am going to, and just so you're aware, I'll explain why I'm allowed to do this in just a second, but this is the sine of theta squared over the cosine of theta squared. And I still have that plus 1 out there. If you like a little note on the side to give yourself an understanding of why I was allowed to do that. I'm not going to be writing anything here, so if you have some space, you may. Or if you can fit it in the middle, you can do that. But this is the quotient identity, so I'll write that first, maybe. Quotient identity. And you say, oh, Mr. V, the quotient identity didn't have any squares in it. But consider the following. If we had the tangent of some angle, and we knew, according to the quotient identity, that that is equal to sine over cosine, then look at what actually happens if I square both sides, which I'm allowed to do algebraically. I end up with the tangent of a squared is equal to the sine of a squared over the cosine of a squared. Okay, so this is really just an extension of the quotient identity, in which case we've squared both sides. Okay, let's continue looking at this left side. And remember, our goal is to get it looking like our right side. So I'm always going to be checking back and forth to say, how am I doing? Well, I notice on my right side that I only have one term. And on the left side, I have two terms. How could I eliminate the second term or combine these two terms? Well, again, I'm going to be applying my laws of algebra, and I can add fractions. How? How can I add fractions? I'm going to use a common denominator. Okay, so what I have to do here, I'm going to run myself out of room with that note, but I've got the sine squared over cosine squared plus 1. And what I'd like to do is express 1 as a fraction over the square of cosine. So if I actually take this 1 and think of it as 1 over 1, and I multiply top and bottom by cosine squared, I will create a fraction that is equal to 1, but that has cosine squared as its denominator. And now I can add them. I simply have in the denominator the square of cosine, and in the numerator I have sine squared plus cosine squared. Ah, now you should be seeing something. You should be seeing another one of your identities. What do you see? Well, sine squared plus cosine squared, according to my Pythagorean identity, is simply 1. So my numerator reduces to 1, and my denominator stays cos squared of theta. And now you're saying, oh, I know a relationship between cosine and secant. They are reciprocal ratios of one another. And by this kind of same rule that we drew out here for the quotient identity, if you were to square both sides, or square all of the pieces, you'd end up with 1 over cos squared of theta is equal to secant squared theta. So the reciprocal of this is, this is equal to secant squared of theta, because they are reciprocal ratios. And we've shown that left side equals right side. If you want to write it there, kind of in the middle as a summary type thing, otherwise just write it right there. And then we can say, therefore, tangent of theta squared plus 1 does in fact equal secant of theta squared. Okay? First example, we were able to apply a quotient identity, we were able to apply the Pythagorean identity, and we were able to use basic algebra skills in a common denominator here, and then using a reciprocal ratio here. Again, always looking back from left side to right side to see which direction we should be going and how we are doing. In example 2, we're asked to prove that 1 minus the square of the cos of theta is equal to sine of theta times cosine theta times tangent of theta. It might look to you like a big mess, but we have the tools that we need in order to solve this. And even if we can't see where we're going, where we're heading, what we're going to end up with, we can ask, okay, what can I do here in this situation? The first thing we can do is set ourselves up with good form using left side, right side. Now, in this example, I can see two things that I can do, and actually working from both sides is going to be more convenient here. The first thing you're going to notice, probably, because you're supposed to deal with reciprocal ratios, in which there are none, and then tangent ratio, which there is, I am going to use the quotient identity over here on the right side. Quotient identity, which changes my right side into sine times cosine times sine over cosine. Okay? Now over here on the left side, I see something else that's helpful to me, but you might not make this connection immediately. This really is just another application of the Pythagorean identity. Okay? Pythagorean identity. Now, if you still don't see it, you're going to want to go back to your first page and take a look at that identity, and maybe even rewrite the identity using two other forms, because if the cosine plus the sine is equal to 1, well, what if I subtracted sine from both sides? I'd get the cosine squared is equal to 1 minus sine squared theta. Well, what if I subtracted cosine from both sides? I'd get that the sine squared of theta is equal to 1 minus the cosine of theta, and all of those just come from the Pythagorean identity. Okay? So what we have here on the left is 1 minus the sine squared of theta, which is right down here. It's equal to the sine of theta squared. All right? Now over here, that's as reduced as we're going to get that left side. So I'll move back over here to the right side, where we see a string of things being multiplied together, but I notice that I now have a cosine in the numerator and a cosine in the denominator. So by basic algebra skills, don't those just equal 1? Cancel each other out, leaving me with sine times sine in the numerator, which is sine squared. And again, we've been successful. Right side equals right side. Sorry, left side equals right side. Therefore, 1 minus cosine of theta squared is equal to sine of theta times the cosine of theta times the tan of theta. Example 3. Example 3 presents us with trigonometric expressions within rational expressions. Okay, a rational expression means it's a fraction, basically with the variable in the numerator and the denominator. Okay, there's no way of eliminating the denominators here, and we're going to set it up, and we'll show you another trick that you can use when you're doing a problem like this. So we've got that the left side is the sine of theta over 1 plus the cosine of theta, And the right side over here is 1 minus cosine theta over sine of theta. Now I'm going to go ahead and look at both sides, and I see this 1 minus cos theta. That's almost like the Pythagorean identity, but not quite, so I can't use that. I can't use it here either. Again, no squared terms here. And this is where we get a bit tricky, a bit stuck. So you're going to want to remember this tool. There's nothing that I can cancel out. There seems like nothing I can really do, but I can actually create a squared term here, okay? And all I need to do is multiply. I'm going to look at the left side, and I'm actually going to multiply the left side by 1. You say, well, that's ridiculous. But remember, I can express 1 as a fraction with anything in the numerator over the same thing in the denominator. So I'm going to just rewrite what I have and restate what I just kind of mumbled over. But what I can do is I can create a squared term using what I know about the difference of squares. So I know that if I multiply 1 plus the cosine of theta times 1 minus the cosine of theta, I'll be multiplying a sum and a difference. I'll be finding the product of a sum and a difference, which is the difference of squares. Okay, and we'll follow that thought through in a moment. First thing I need to remember is that I'm multiplying by 1. So I need to use the same value in the numerator and the denominator. So I haven't changed the value of the left side at all. They've simply multiplied by 1. But watch what that does. Now in the numerator, I have, right, multiplying fractions, top times top, over bottom times bottom. But look at what happens when I set up that bottom times bottom. It'll be a little bit easier for you to see in this format. I've created a difference of squares, okay? So I'm going to make a little note there. We want to create a square term by multiplying by a fraction equal to 1. Okay, again, that's not something that's immediately evident to you if you've never done problems like this before, but now it's a tool that you have that you can use as you move forward in your practice problems. So let's go ahead and simplify this left side a little bit further. We have sine, and you might think, okay, I want to distribute. You might think, yeah, you need to distribute the sine to both terms. Hold off on things like that, because look at what you're actually creating in the denominator. You're actually creating a Pythagorean identity. So what's going to happen in the denominator is actually this 1 minus cos squared theta is going to turn into the sine of theta, okay, using the Pythagorean identity, in which case we want to have a sign up here. We'll be able to cancel out. So if you can start to look ahead and see ahead, that's really helpful. But we're going to leave our numerator the same. Our denominator, using the difference of squares, ends up as 1 minus the square of cosine of theta. And now we can apply Pythagorean identity. And the denominator, numerator stays the same. Our denominator simply reduces to the sine of theta squared. Reduce that one further. My sine, one of the factors of sine theta from the denominator is going to cancel out my sine theta in the numerator. It's going to leave us with 1 over the cosine of theta over the sine of theta. And look at that. I believe that's what we have on the right side. So left side equals right side. Therefore, the original statement, sine of theta over 1 plus the cosine of theta is equal to 1 minus the cosine of theta over the sine of theta. So you have a handful of tools that you can use there: the Pythagorean identity, the quotient identity, which replaces tangent with sine over cos, the reciprocal identities, which replace any secondary trig identity with its reciprocal primary trig identity. And then we use our algebra skills in order to reduce, multiply, add, divide, distribute, all of those things. Okay, so go ahead and try the practice problems that you have outlined for you today. They are from page 273, numbers 3 through 8. And then as an extension to that, we'll spend a whole nother day for you, maybe a couple hours of practice, working on the proofs that are on the next worksheet, on the next page in your notebook there, the trigonometric proofs worksheet. Ask questions anytime, and go ahead and try your problem solving skills at that.